Some don't.
Okay.
Yeah. Some people think it's worth doing just to help somebody out. So, okay, we're going to finish up chapter 6 today and continue into chapter 7. I think we're easily on track to have chapter 7 completed before the exam next Thursday. So we'll do just a couple of slides of it today. Chapter 7 doesn't have near as many calculations as what was in chapter 5 and chapter 6. So there's just a lot of lecture to go over in those slides. There's a lot of pictures in chapter 7. Those slides are going to go really quick. So I think we're on track to be where we're going to be. Once I get an idea of where we make it through today, and if I think we can make it on Monday, I'll post a study guide. So I'll have that out there. The old exams are there. The thing I'll tell you, if you want to start going and looking at exams this week, there will be some exams where chapter 7 material is on exam 4. And you're just going to have to look at the exams to see where it lines up at. Because this is the first time we've ever tried to get through chapter 10, the first semester. So a little bit different this year. Usually we did in the last unit, we did at least half of chapter 7, chapter 8, and chapter 9. So this is different. Okay, so we're going to keep talking about these things. We're talking about how we can calculate enthalpy of reactions. And the last thing that we talked about is that we have the standard enthalpy of formations. And we talked about how to put these things together, and we could form these different reactions and find out the enthalpy for an unknown, like we did in this example clicker question. The thing is, we can use this enthalpy of formation, and we realize that for things that are in their elemental state, all right, so their standard state conditions, to make 1 mole of the pure compound, that's what the enthalpy of formation tells us. So if we go back and think about one of these substances, we're going to make water. The enthalpy of formation would be the combination of hydrogen gas and oxygen gas, the two elements in their pure form, to make water. And when it does it, it releases 285 kilojoules per mole of energy. And that's what every one of these represents. That's the reason the things that are in the elemental state already, like oxygen, like silver in its elemental state, those things are all already zero. Because you're not forming them from anything, that's the starting point. That's the ones that are all zeros are the starting points. And anything deviating from that is a non-zero. Some are endothermic, some are exothermic, some are positive, some are negative in our systems. So anything that's that has a delta H of formation of 0 is an element that's in its standard state. You find the one that's in the 0. And because we're going to make 1 mole of compound being made, it may be the reactions are fractional. All right, so if you're, depending on what the number of atoms are, if you've got something that's a diatomic, you may have to use 1/2 of that in something. That's fine. So whenever we write these formation reactions, what we need to do is take the elements in their elemental states, like carbon and oxygen, to make carbon monoxide. The phases become significant. So if we look at carbon, there are several forms of carbon, but there's only one that's graphite that has a delta H formation of 0. That's the one that we want to use. And then oxygen standard state is a diatomic. So if we put together the carbon form of graphite form of carbon, the diatomic oxygen to make CO, we'd see that it's not going to be balanced because I've got 2 oxygens on the left and I've only got 1 on the right. So the way that I could correct that so that I get the proper amount of product that I need is I just have to put the 1/2 in front of the O2. Now that gives me a balanced reaction that I can look at. So when I look up the table and find out what the enthalpy of formation for CO is, I need to realize, I'm going to go find that for CO, that this guy, this negative 110.5, is representing this reaction at the bottom. It's the graphite form of carbon plus 1/2 in O2 yields CO gas. So what do we do with these? Well, we can put them together as we've done previously, and we can add together enthalpies for known steps, okay? Because enthalpy is a state function, we can take things that are known, add them together, and find the entropy of an unknown. The thing that we want to use are shortcuts whenever we can. So the shortcut that we're going to learn to use is called Hess's Law. And this is Hess's Law. It says the enthalpy of a reaction, and the little zero means standard state, is the sum of the enthalpy of formation for all of the products minus the sum of the enthalpy of formation for all of the reactants. So whenever you see this capital sigma, Greek letter sigma, that means to add up or to sum together. And N just represents the coefficient in front of the balanced reactions for the stoichiometry. So to utilize this equation, all I have to do is go into this table, and I have to find out what are these enthalpy terms. So what are the enthalpy of formations for all my products and all my reactants, and just put the numbers in. And we're going to do a couple of examples of this, and we're going to do these the old way that we were doing. And when I say the old way, the previous way, where we had to spin all these things around and make them add up and cancel out, versus we're going to apply Hess's Law. So the first one we're going to look at is methane. So I'm sure I got the right one here, I do. So methane reacts with O2 to make CO2 and water, and the stoichiometry is 1 to 2 to 1 to 2. And if I think about what's happening in a fundamental state, what I'm going to do is I'm going to take these starting materials and I'm going to decompose them to the individual atoms. So if I break all the bonds and break it apart, I end up with carbon, hydrogen gas, and oxygen. Okay? And then I'm going to start forming the things together. First thing I'm going to do is take some of the carbon and some of the oxygen, and I'm going to make some CO2. So I'm going to form the CO2. And if I think about that reaction, it's the carbon plus the O2 yields the CO2. And I look up in the table, and I find it's a minus 393 kilojoules per mole. And then I could look at the other thing I need to do is I need to come to the product that I need, for my reaction. I got the CO2 made now. Now I need to make the O2. So I'm going to take some more of the hydrogen and the oxygen, put those together, and to make O2. So now those two things are going to come together and make the O2 for me. So hydrogen plus the half of an oxygen yields O2 gas. And I look up at the table, and I find it's a minus 241.8 kilojoules per mole. So I take the enthalpy of formation for the methane. This is the one that I had to think in terms of it. I'm not making methane, but I've got to get it apart. I've got to break it. So the enthalpy of formation for the methane, it'd be the carbon plus 2 hydrogen gas, and I look it up in the table, and it's a negative 74.6. So all of these things, these values come from the table. And we just have to realize what these are represented in terms of reactions. So now the challenge is to figure out how to add these three things together, 1, 2, and 3, so that they give me the enthalpy of formation for the reaction I want. Methane plus oxygen yields CO2 and water. Okay, so one of the things I see is we start trying to figure out what goes where. Is I look at the things that are products and the things that are reactants, and maybe what's going to stay the same and what's going to have to be spun around. Okay, I know I want, in this reaction, there's no carbon in the form of graphite carbon. So somehow I've got to get the carbons to cancel out. And if I look at the methane, the only place that I find methane, it's a product, and I need it as a reactant. So I know this one's going to have to be inverted. So if I invert it, that means the carbon in the form of graphite is going to be on the right-hand side. So maybe the graphite's okay here. Now, the other thing that I see is that the CO2, if it stays here, there's going to be some CO2 where it needs to be. There's 2 waters on the right, and if I look at the only place that I find water in this, I only find 1 water on the right. So whatever's in this one, I'm going to have to multiply everything by 2 to come up with 2 waters.
You would just have to positive 7.
Yes, okay. When we switch it around. So that's exactly what we're going to do on the next page.
It's like C4 produces.
Okay, that's what we talked about on these are the elements. So whenever I look up in the table, so I'm going to run back to the table. All right, so methane. I find methane in here. So methane, it's this guy. This is the enthalpy of formation for methane. So what it's coming from, that reaction, is the combination of methane, or the carbon in the zero state. All right, so solid graphite. The only other element that's there is a hydrogen, so plus H2. So H2 gas yields my product, methane, in the gaseous state. And to make it balance, I need two of them there. So all I did is take the compound that I want, and I add the proper number of the elemental atoms together to get it. So I'm looking up the things that are zero. So this is the zero form. Change my color so I can see them line up. This is my zero form of the carbon. And if I find the hydrogen gas, it's in here somewhere. It's my H2. This is the zero form of the hydrogen, H2 gas.
So what's the oxygen form in it?
Okay, so the oxygen, going back to where we are. All right, so the oxygen is making the CO2, and it's also used to make the water.
So you take the reactants and then you figure out what composes them? Is that what you're saying?
Well, I'm going to take every component here that's not an element, and I'm going to have to figure out the energy that it takes to make it. So I'm taking out, how would I make methane? And put it together from its individual atoms. O2 is already there, it's in an elemental state. How would I make CO2? So put it together from its individual atoms. That's what this one's doing.
Yeah.
Exactly. So what we're doing here is taking my starting materials, my reactants, and I'm taking the amount of energy that would take to make everything to an element. Break all the bonds. Get it in the form of an element. So, and then I'm going to take and go the other way with it. I'm going to put all the free elements together to make the products that I want. Okay, so that's the basis of what we're doing. All right, so now I can come up with these different things, and I can figure out where I need to, which ones I'm going to have to spin around to get them to add together to come up with this thing at the top. And we said we've got to spin around number 1. We're going to use number 2 as it is, and we're going to at least have to take number 3 and double it. All right, so if we do those two things, we spun around number 1, and it was a negative value on the previous slide. Now it simply becomes a positive. If I take the bottom one and if I multiplied everything by 2, that was 1/2, it becomes 2. This number was 200 and something. Now it's 400 and something negative. Okay, so now if I look what things cancel out and give me what I want. So let's look what's common and cancels out on both sides. So the graphite that is on the left-hand side of the second equation cancels out with the graphite that's on the right-hand side of the first equation. Okay, that looks good. The two hydrogens that are on the right-hand side of the equation number 1 cancel out with the two hydrogens on the left-hand side of equation number 3. Okay, that's good. So the things that I'm left with are the methane. So I'm going to drop it down. I've got 1O2 from equation number 2, 1O2 from equation number 3, so that gives me my 2 O2s. I've got a CO2 and 2 waters. That's exactly what I want. So now all I have to do is to add these 3 things together. So I sum all those together, and the delta change in enthalpy for that reaction is negative 802.5 kilojoules.
Are there like any practice?
There's a bunch of them in the book, and we're going to work some more of these in a minute.
Now, why you do all this to get the enthalpy of that reaction?
That's the goal of this was to find is what is the enthalpy of this reaction.
So why can you not just use the chart just to look at the CO2?
That's exactly where these came from.
So what do you have to do all this flipping around?
Well, if you want to understand how those add together, that's the way that we add them together. So I'm showing you this, so I want to show you Hess's law, which instead of doing it this way, Hess's law says we just take the summation of the products minus the summation of the reactants. And I think you're going to see this is a much easier way to do it. Now this is the table. It's in much too fine a print here, so I went to the next page. So I need to look, what are the products? The products are CO2 and 2 waters. So it's going to be the enthalpy of formation of CO2 plus 2 times the enthalpy of formation for water, and then minus that of the reaction. So I've got a set of parentheses. All of this is going to be inside these parentheses. And I look at my reactants that I have. I've got the methane, so I need the enthalpy of formation of the methane and that of the O2. So 2 times the enthalpy of O2. So now what I do is I've got the equation set up. I just need to go to the table and look up what are these values. So I'm just going to jump forward to the next table to show where these come from. So the first one I need to look up is what is the enthalpy of formation for CO2. All right, so I'm going to look that guy up, and I find CO2 in the table. So here's my CO2. It's a negative 393.5. All right, so I put that value in, negative 393.5. And now I need 2 times the enthalpy of formation for water. So I go to my table and I find my water. So water, okay, here it is in the gaseous state for water. It's a negative 241.8. So negative 241.8 times 2. Now that closes this sets of parentheses out. So that's all of the products. Now I've got to subtract the summation from the reactants. So it's a negative, subtract, and I've got to find my methane. So find my enthalpy of formation for my methane. It's going to be under carbon. So carbon, and here's methane. It's the one that we just did. It was a minus 74.6. So a minus 74.6. Then plus 2 times the enthalpy of formation for the oxygen. We'll go into the table and look at it. But I know since oxygen's in an elemental state, everything that's in the elemental state is 0. So this term is 0. So it drops out. It's not even significant. So now when I do the math, just take this, multiply it by 2, add those together, and subtract this number from it. I get exactly the same number, the negative 802.5. So essentially what this is doing is what you're saying, taking the values from the table and adding them together. Hess's law, which one's easier? I think this is a whole lot easier than all the stuff that you had to do to get this, switch them around, add that together. You can do either. They're using the same information. You're using the information that comes from this table. Hess's law is a great shortcut to use. It's just the summation of the change in formation from the products minus that of the reactants.
So on the test, that be given to us, or
absolutely, it has to be. I'll either give you the table, or I'll give you the enthalpy of formations for the compounds that are needed. I think typically I'll give you a list of enthalpy of formations. Now, what I'll do sometimes is, when I typically do it, is I may give you 5 or 6 enthalpy of formations, and you only need 4 of them or 3 of them. So I'm not going to say you got to use every number in this calculation. I want you to be able to disseminate to some extent. If it didn't waste so much paper, I'd get picture the table out. But I'm a little bit paper conscious on how much paper we waste. So this can do a lot of things in here, but if we want to do something that's a unique compound like hexane in a reaction, hexane's not in here. Or octane's not in here. Propane's in here. Acetone's in here, but some of the larger hydrocarbons are not in here. Glucose and sucrose, they're in here. But this is what's just in this limited table. Okay, so let's do another example of this. So calculate the enthalpy change for the combination of C2H2, that's acetylene. 2 of those plus 5 O2s yields 4 CO2s and 2 waters. So the first thing I'm going to do is do it the standard way. So I'm going to take and look at the energy it takes to break up all the acetylenes and find that in the table. So that would be the graphite plus the H2 yields the acetylene, and it takes 2 graphites to make it balance out, because I got 2 moles of carbon on the left, need 2 on the right. I look up in the table, and it's a positive 277.4. If I look at making the CO2, the energy that's going to be involved with making that molecule, we've already did this one, carbon plus the O2, and its value was a minus 393.5. And we've done the water as well already, H2 plus 1/2 in O2 yields a water. Its value was 285, negative 285.5. So I could try to figure out how to rearrange those, and I could do that. Let's see, what would I probably have to do? Well, I know this one's going to have to be, the top one's going to have to be switched around because this is a reactant in my reaction here. So I'm going to have to take this top one and spin it around. And if I do that, let's see what that does. That would put it on this side, but I need 2 of them as well. So I have to multiply it by 2. When I multiply this guy by 2, it's 2 times that. Then I'll look at the other one that I'm going to have to do is when I take and spin this one around and multiply everything by 2 on this one to come up with 2 here. This times 2 means I'm going to have 4 carbons I'm going to have to cancel around. So I'm going to have to take everything in this second line. We'll call this one equation number 2. I'm going to have to multiply everything in it by 4. 4, 4, 4. So multiply that one by 4. And then I can use the water one as written, except I need to come up with the 2 waters. Right? So I've got to multiply everything by 2. So here's the 2 here. Now if I cancel things out. So I should be able to. So the 4 carbons and the 4 carbons cancel out. The 2 hydrogens on the right, 2 hydrogens on the left cancel out. So that gives me my 2 acetylenes. I've got 4 oxygens and 1 oxygen give me 5 O2s. And I've got 4 CO2s. And then the last thing is the 2 waters. 2 waters. I just multiply these terms through, then add everything together. I get a negative 2,600 kilojoules. That's the hard way of doing it. Now let's do it with Hess's law. Hess's law says it's the summation of products minus reactants. So I've got 4 times the enthalpy of formation for the CO2, plus 2 times the enthalpy of formation for the water, minus 2 times the enthalpy of formation for the reactants, which is the acetylene, plus 5 times the enthalpy of formation for the O2. And O2, I know, is 0. So that's this term. It's not even significant. So all I have to do then to do this is go look up these enthalpy of formations for these 3 things and plug it into the equation. All right, so I go find those things. So the first thing that I need to find it for is for the CO2. And we just did the CO2, but I'll highlight it again for you on this table. So find carbon, CO2, it's the negative 393.5. All right, so 4 times that one. The next is the O2. We just did the O2 as well. So O2 was a negative 241.8. So 241.8. And then the last thing is the acetylene. So I'll find the acetylene. So C2H2. So C2H2 gas is a positive this time, 227. So a positive 227. I multiply it by 2, and I take this and subtract from everything that's here, and I get a negative 2,600 again. Go backwards, same value. Which one's easier? Hess's law. This is a shortcut that you need to understand what the other's doing. It's breaking everything apart at the atomic level and then recombining the elements to make the compounds that you want. But Hess's law says it doesn't matter how we get there. It just matters what you start with, your reactants, and what are the products that you form. And as long as I know the energies associated with both of those, I can add them together. Yes?
And it's negative because, like, change the products. Yeah.
Well, the flipping is on this form when you put them together this way. On this one, there's no flipping. Yeah, it's taking that. Only thing you have to realize is that these are your reactants. What's on the left-hand side? Right, so that's this portion of it, and the other side are your products. What's on the right-hand side? Okay, so that's this portion of it.
When we do draw, we use this.
You can use it, yes. If you've got the data in the tables, you can apply Hess's law to this every time. And it certainly makes life easier.
We're gonna find that line sometime in the future.
Unless you don't have the value in the table. The only way that you would want to use the other is that if you didn't have one of these and you had to go through 2 steps together to make it. And that's a possibility. And that's the reason we go back and we have to use this old rigorous form sometimes, is that sometimes I don't have these guys. If these are not known, I have to figure out another way to get there. Okay? All right. So let's see what we got next. So, look at that. Surprise. It's a group. Talk about it. Use Hess's law. You've got all the enthalpies that you need in this little table. Products, mass reactants. Should be simple. Couple of minutes. All right, another minute. I'm not talking about it much.
I didn't write it all down, but.
Seven more clickers. All right. Last 3. Last 2. Survey says most of you think it is choice C or choice E. Choice E. Okay, so I'm just going to quickly go over this. So products minus reactants. So the enthalpy of formation, enthalpy of formation is products minus reactants. So on the product side, I've got the 4 times the value for CO2 That's the one we've been using, minus 393.5. Parentheses, plus 6 times the value for O2, and the O2 was the minus 241. Say again? It's for gaseous, 241. That's for liquid. That's very good. All right, so 285.8. All right, so that's all of the products. Then of the reactants, the oxygen is elemental, so that one's going to be 0. I don't even have to worry about it. It's 2 times the value for methanol in the liquid state, ethanol in the liquid state. So minus 277.6. Add it together, and you get the minus 2743 kilojoules. All right, now this is an example where you really have to look at the states, because we've been doing water and the gaseous on the previous problem. This one says liquid, and those two things have different enthalpy of formations.
So why do that?
The difference in the two is the energy of condensation, the energy required to take from the gas into the liquid. Okay? Question on that? Most of you got it? All right, just a couple more slides in this chapter. So the last couple of things I want to talk about are energy consumption and things that are going to impact us in the world around us. So I talked about fossil fuels. Fossil fuels are the result of long-term energy storage. So if we think of fossil fuels in its most fundamental sense, fossil fuels are the result of photosynthesis. Plants grow, something eats the plants, they die, decay, gets buried, slowly gets converted into the hydrocarbons we use as fossil fuel. But that energy came from sunlight. If you want to think of it, the fossil fuels are the battery that stored that energy, that chemical potential energy. But that process to create that energy was captured over tens, if not hundreds of millions of years, all right? And then it was put in the ground through the decaying process, which took hundreds of millions of years. So fossil fuels that we're consuming now came from things that were alive several hundred million years ago. And it takes that process of a couple of 100 million years to replenish those. All right, so, I mean, it seems not right to think about it, but it will be the fossil fuels of 200 million years. The living things of today will be the fossil fuels in a couple 100 million years as your body decomposes. Okay? If we look at the rate that we're consuming this stuff, and it's somewhere between 50 and 100 years, we're going to have depleted the world's supply of fossil fuels. Now, there are other things that say that's going to be longer, that it may be 200 years. It depends on what is the cost and what is the environmental cost. There is oil in a lot of places, but if it costs more than the value of the oil to get it out of the ground, it's not economically sensible to go drill and to extract that oil out. Over 50% of the wells that are drilled in the United States are capped off. They find that the oil's there, that oil field's there, and they never extract the oil out. They're waiting for the oil market to go up high enough that it's feasible to go get that oil out. Right? But at some point, your lifetime, your grandkids' lifetime, their grandkids' lifetime, we're running out of fossil fuels. There's just no way around that. So where do we consume it today? Making our homes comfortable is about 20% of the energy we consume. Commercially consumes a little bit less than 20%. Industrial, making the things that make our life good, are the biggest consumer, and we go everywhere in the United States. So transportation, especially for those of us that are in the rural environment, you talk to people in large cities, they don't own a car. Okay, so my friends that moved from Oklahoma to Boston to go to graduate school, an apartment with a parking place was $2,200 a month. the same apartment building, if it didn't have a parking place, it was $1,500 a month. $700 a month for a parking place. So they got rid of their cars, they couldn't afford it. But it depends on where you are. Is there mass transit available? That's buses, rail systems, whatever it is that give you the transportation you need? Or do you do like some countries, you ride a bike? Okay, so there are ways to get around without starting the car up. We just have to be willing to do it. So that's where we consume most of our energy, and here's how that's changed, at least in the last 70 years. So we are certainly in the United States have a petroleum dependency, and it spiked in the 70s and then went down with we had the oil crisis in the 70s. But as the population has continued to increase and we continue to have our love affair for automobiles, we burn more and more fossil fuels. In the United States, the population is in the neighborhood of, it's hard to pinpoint exactly what it is, but it's 230 to 240 million. We have more than 230 million cars on the road. Okay, there is more than a car for every person in the United States. Some people can't drive. So do we really need that many cars? Some families don't have a single car, and other families have 3 cars for every person. All right? We just consume petroleum like crazy. What do you think caused this little drop? So starting in year 2000, the fuel that we consumed, petroleum, started to drop. And it's actually starting to go back up now. What do you think caused that drop? I remember it well. It's $5 gasoline. So, okay. So in 2000, 2001, I bought it was actually 2000 when I bought it. I bought a Ford F-150 Super Crew 4-wheel drive, 5.4, 12 miles a gallon. And 2 years later, gas was $4.60 something here a gallon. And I got a Mazda 6. And I've always kept a truck. In fact, I've still got that same truck. It's almost 20 years old, and it's barely got 100,000 miles on it, but I only drive it when I need it. Okay, we have to get to save energy. We have to decide, does grandma by herself really need to be driving the Suburban? Or one person in the vehicle really need to be driving the Suburban? That's where you make personal choices that are going to turn this path around. If gasoline hits $10 a gallon, has anybody ever been to Europe? Did you look at the price of gas in Europe? It was in liters, cost per liter. Didn't pay attention to it. In Europe, they pay about 3 times per equivalent gallon what we pay in the United States. Go to Japan. Japan pays over 10 times per gallon what we pay in the United States. Okay, so their choices become economical choices. The cost of fuel is so high that they don't consume it like we do. Most of the natural gas we consume goes towards our electricity. There are a few natural gas cars that are available now. In fact, there's Love's or somebody just announced that they're going to start doing a natural gas outlet. There's several car companies that of the big car companies that are giving a natural gas option. Natural gas burns a little cleaner. Your engines last longer. Not as much bad stuff comes out of the tailpipe. So it's still producing CO2 in the atmosphere, but there's not as many bad things, other elements, not as many heavy elements and other things that are there. Coal is just our steady climb. It had decreased through the Obama administration, with the EPA put some more stringent guidelines on the emissions of coal materials, but all of those were just dropped, so that number is going to be up here in 2 years. Okay, because we said we don't care the emissions that come out of the smokestack. If you live in Fort Townsend, you do, because you don't want mercury coming out of the top of that smokestack raining in your house and in the fields where your kids are going to play. All right, so there needs to be some common sense on the coal. Coal varies a lot in its purity, and that's the big thing about coal. Oklahoma used to have a lot of coal mining that was done, and it was used primarily to heat homes with And there's a big strip mine on the other side of Wilburton that you can see. The remnants of that monster machine, that shovel that was used. There were other places in Oklahoma, and there's a lot of coal in the ground. It's contaminated with heavy metals. We use that coal and we burn it. Those heavy metals go in the atmosphere, and they're going to come back down. They're going to end up in our drinking water or wherever else they're going to be. Renewables have always been around. Some people heat their home with firewood, and that's all they use. Okay, but it's still a pretty low percentage of the energy that we consume, around 10% or less. Nuclear reactors started to go online in the 60s and have been on a slow, steady increase in the United States. The thing with nuclear is we haven't built a new nuclear reactor in over 20 years. And after the incident that happened in Japan with the tsunami and that tsunami wave hitting the nuclear facility, and it caused core damage and it caused some radiation to leak out, we've stopped the production on the facilities. Nuclear, if contained, is the cleanest option. It's the only one except the renewables that doesn't produce CO2 into the atmosphere. Okay, what are we going to do in the future? I mean, that's our question. Especially, what are we going to do when we eliminate at that 100-year mark, 300-year mark, or 400-year mark? When these guys are gone, what are we going to do? Okay, there's going to have to be something, and somewhere we're going to have to invest in what that something's going to be. So one of the problems we have with fossil fuels is not just the fuel themselves. The fuel themselves is going to yield the CO2 problem, but it's the additives and impurities that we put in those that lead to harmful materials as side reactions. So things like sulfur dioxide, carbon monoxide, the NOx's that exist, and ozone. Now, a lot of these were corrected by the addition of a catalytic converter. So in the 1980s, the EPA required that every new vehicle sold in the United States had to have a catalytic converter. And I tell this story. I went to LA to a funeral in the 1970s, and I was a little kid, and I remember we drove there as a family, and we're coming over the mountains, and we're looking down in LA, and all I see is this brown, reddish-looking haze. Can't even see the city down below. I'm going, what the heck? Is there a fire? And I'm asking my dad what's going on, and that's LA. Problem was is that everybody had all these cars that produce NOx's and all these gases from the gasoline. It went into the environment and the atmosphere, and those gases didn't break down, and that's what smog is. You have the problem now if you drive south. Dallas is the LA of today. The state of Texas said that inspection stickers are no longer necessary, so the state of Oklahoma. And people can cut off their catalytic converters if they choose and replace it with a piece of pipe. And those emission gases, the catalytic converter's job is to destroy all these things so they don't come out of your tailpipe. These are all side products of internal combustion motor. It breaks the sulfur dioxide down into elemental sulfur and oxygen. It breaks carbon monoxide, converts it to CO2. The NOx's it converts to nitrogen plus oxygen. All of these get converted into harmless forms. That's the catalytic converter's job. Some states have decided that's not important. And I moved here from Missouri. I grew up in Oklahoma, not far from here, but I went to Missouri after graduate school and worked for a company. And in Missouri, in St. Louis, you had to take your car and basically get an enema every 6 months. So to control their smog population, the city of St. Louis at that time had a greater population than the state of Oklahoma. Every 6 months, your car had to go to a gas station, and they would stick a probe up your tailpipes in your car to make sure it produced none of these gases. If it produced those gases, you had a 1 week warning to get it fixed. After that, they took your tag away. All right. State of Texas right now is the biggest violator of this that we have. Such a big state, and everybody in Texas has 4 cars. Right? Everything's so spread out. You've got to have individual transportation to some degree. But the emission standards in Texas are, we're low in some things in Oklahoma, but Texas is the one state that's fought the federal government the most on emission standards. Rick Perry and President Obama literally got into a war where Texas was going to secede from the Union over emission standards, and the U.S. government ended up backing down, but they were going to pull their funding from it. What can you live with? And one of the things that you have to remember, the United States is a couple 100 million people. So we're less than 300 million people out of a world population that's 7 billion. We're 5% of the world population. Everybody else is going to do something too. And the problem is we're one of the, if not the most advanced society in terms of the way to consume energy. When the other, let's say the other 50% decides they got it pretty good there in the States, let's live like that, then the world's really going to have a problem with CO2 production and these emissions. It's just part of the things of life that we're, as a society, going to have to figure out how to deal with and how to face. All right, that's chapter 6. Let's roll right into chapter 7. So save that one. So chapter 7, new topic. The topic is looking at quantum mechanical model of an atom. And again, as I told you, this chapter is going to go pretty quick. The notes have been posted on this one a while. So we're going to look at what quantum mechanics mean. We're certainly not going to do any quantum mechanics because that takes very, very advanced mathematics. But we can talk about the outcomes of quantum mechanics a little bit. We're going to go back and re-talk about a little bit of the history that we talked about of the atom, the things we talked about way back in chapter number 2, and revisit what those mean. The nature of light and how it behaves as a wave, the electromagnetic spectrum and what that means, something called interference and diffraction and how that applies to atoms, and then the crazy side of light is that sometimes it's a wave and sometimes it's a particle. Okay, so we're going to talk about the duality of light. Then we're going to talk about atomic spectra and the Bohr model and how Bohr came up with a mathematical model to explain what we see with matter, and the wave nature of matter, something called the uncertainty principle that goes with quantum mechanics. And then we're going to talk about, finally, where electrons are in atoms. The only thing that we've said at this point is there's some distance a long ways from the nucleus and there's a lot of empty space. Now we're going to try to figure out where they're actually at. We're going to introduce what quantum mechanics predicts as a set of quantum numbers and how these orbitals have shape associated with them. Not many problems to look at in this, and this is one of the shorter mastering chemistry assignments. So it's only going to take you, should take on average only about 40 minutes to work that problem set from Mastering Chemistry Chapter 7. So it's going to be due a week from today, next Wednesday. Right? So that's a short one to do. I encourage you to do it. Some of you still need to do Chapter 6 because less than a third of you have completed it at this point. I looked right before I came into the class. Okay, so diving into this chapter. So beginning of quantum mechanics. If we go into the beginning of the 20th century, so in the 1900s, what we were looking at was purely physical phenomena. Things that we could see and measure and touch with our hands, measure with a ruler, measure with a balance, and we thought that was the thing that predicted all of the behavior associated with matter. At the same time, in the 1900s and the late 1800s, there were many famous physicists that are trying to figure out what's happening inside of an atom. They're looking at these subatomic particles, and what they determined is that what's happening in the present doesn't always determine what the future is going to be. And that's the basis for what quantum mechanics tells us. And the people, you may have heard some of these names, but the contributors were Albert Einstein, everybody's heard of that. Niels Bohr, we talked about in the early part of the semester. Louis de Broglie, Max Planck. Max Planck is the physicist who went and got Albert Einstein out of the patent office because he read one of his papers and said, this is brilliant. At that time, nobody would even give Einstein the time of day. He was making the equivalent of minimum wage at that time. Werner Heisenberg, great contributor to quantum mechanics, Dirac, and Edwin Schrödinger, who came up with the first solution for an atom. All right, most of this is occurring in Europe. The educational system in the United States is just starting to be developed at a high degree at that point. So quantum mechanics is our foundation of chemistry because it explains the organization of the periodic table. Why do those elements get in certain groups and families, and why are they organized the way that they do? It explains the behavior in elements in terms of the chemical bonding that they have. So why do some things form a covalent bond? Some things form an ionic bond. We can explain that with quantum mechanics. It gives us the basis for things that make life great. Lasers. The fact that we use lasers now is the standard way that we communicate. In the olden days, if you ever talk to anybody overseas, and before the advent of laser and a fiber optic laser, the signal was transmitted from a wire signal to someplace like at maybe Houston. That signal is beamed to space. It went around the Earth in a series of satellites. That signal came back down to the Earth, and then there was a wire went back to wherever that phone receiver was. And literally, you ask somebody a question, and the signal had to go everywhere. And even moving, and as fast as electrons could move in an electrical wire, there was still a 3 or 4 second delay. All right, so there was a pause in it. Now, signals go in with fiber optic cables. Your voice is converted to a fluctuation in a light signal that transmits across the planet at an amazingly fast rate. Speed of light could go around the circumference of the Earth 3.5 times in a second. So now the delay is almost instantaneous anywhere in the globe. There's no delay. The applications in computers have made your computers so much faster, it's unreal. So we have to go back and think about what the things that make up an atom are. So there's the electrons, which we said were terribly small. They were 1/1640th the mass of the lightest element. Okay, so the hydrogen, the lightest element. If we think of how small they are, a single speck of dust that you can see has more electrons in it than the number of people that have ever lived on. Okay, so there's about 7.6 billion people alive now. There's been about another 6 billion people lived and died through human history, but there's more than that total number together of electrons that's in a single speck of dust. In fact, probably by a factor of 1,000. There's just they're so small it's hard to conceive. In fact, we can't very easily. But it's the behavior of an electron and what the electrons do that tell us what's going to happen with an atom. If I take a penny out of my pocket, I don't have a penny, so can't show you a penny, but if I had a coin and I lay it down on the table, is that coin going to spontaneously react with air and explode? Some elements do. Okay, if I took francium out and took some francium, it's a liquid at room temperature, it's also radioactive, let's go with cesium. Put some cesium on the table and expose it to air, instant combustion, explodes. Okay, why? It's the behavior of the electrons in that atom. Right? But if I took some copper and a penny, lay it out, slowly over a period of years, it's going to oxidize and turn green on the outside. Right? So it's the behavior of the electrons that determine the reactivity of atoms. And we can't see electrons directly. We can barely see atoms using electron force microscopy, and we can make an image of where atoms are, but we can't get smaller than that. So these electrons are the speck in the size of an atom. We can't see individual electrons at all. So the fact that we can't see them makes it tough. Even if we took and tried to illuminate an electron by shining light on it, that would influence what's happening to the electron. It's just so small. So what the quantum mechanical model does is it comes up with a way of rudely or crudely explaining that electrons exist and how they behave in atoms. It comes up with a way for us to understand and predict the properties of atoms, and that's directly related to what's going on with the electrons. So the properties that we have. Why do all the halogens behave the same way in the 7A family? It's because the number of electrons each atom has. and where they lie in the orbitals, as we're going to learn to go in this chapter. So that's the thing that controls the chemical reactivity. That's the important stuff. So why do some elements behave as metals and others behave as nonmetals? The electrons determine. Okay, how many electrons does it have? Does it like to gain electrons or lose electrons? Why do things in the 1A family want to gain 1 electron or lose 1 electron? Things in the 2A family want to lose 2 electrons to form +2 cations. The same when you make anions. All right, why do things want to make a -1 like the halogens, and things like oxygen want to make -2? Okay, why, as we mentioned before, are some elements very reactive and others practically inert, like the noble gases? And then it also lets us understand the patterns that we see that are called the periodic laws and the repeating properties of elements throughout the system. So it's important. All right, we're going to start with the nature of light. And we describe light in terms of its classical way. Light is a wave that's permeating through space. So light, when we say light, we're talking about visible light. So let me put visible in front of this. What we can detect with our eyes, right? It is a form of electromagnetic radiation. And I'll abbreviate that EMR, and you'll see the text does that as well. So what it does is it's composed of a perpendicular oscillating wave that's moving through space, and it has an electrical field in one component and a magnetic field in the other component. So if we think about what that means is that you've got going along some axis here, you've got an electrical component that's going up and down in terms of what we think of as a classical wave, and there's a magnetic component that's moving perpendicular. So if this were the y-axis, the one coming out on the board with the blue we think of as the z-axis, so this would be the z-axis. This one would be the magnetic component. And the key thing about it is that they're at the maximums at the same point, and they're at the nodes at the same point. So they're doing the same things, just in opposite directions. Okay? All right, so there's the two components that are coexisting. The electrical, magnetic or electrical fields is where electrically charged particles experience a force, and the magnetic field is a region where magnetized particles see a force from it. So light influences both magnetic particles as well as electrically charged particles. And the thing that we think we understand about all electromagnetic radiation, we haven't disproved this yet, is that all waves move through space at the constant speed. And more properly, this should say they move through vacuum. Right? If there's matter there, light slows down. But if there's nothing there, if you take the matter out of it, the speed of light is moving the same absolutely anywhere on the Earth. And as far as we can understand, anywhere in the universe, and that speed is limited. There's an absolute governor or speed limit on the speed of light, and it's moving at 3.00 times 10 to the 8th meters per second. Right? And that's as fast as light can go. If you, one of the things that Einstein talked about when he was trying to understand this is that what if you were riding on a beam of light and you were on the front of that beam of light that's going through the space, and you tried to jump out forward? So you'd be going the speed of light plus however fast you could jump. And the thing was that you couldn't jump. So there's a lot of things in quantum mechanics that start to become hard to understand. What Einstein came up with as theory of relativity is that particles start going faster and faster and faster. They start to get heavier and heavier and heavier. So something that weighs micrograms at non-moving, as soon as it starts to approach the speed of light, and it gets to 99% of the speed of light, that micrograms is like 1,000 times heavier. And if you get it to 99.99 times the speed of light, it's like it weighs several tons. And you can't push enough force to make it go faster than the speed of light. You read some of the things on relativity, you can get a better understanding of that. All right. Now, if we look at the way that we see energy transitions that occur, and we think of something like a lightning strike. So, a typical day in a thunderstorm, sound travels at about 340 meters per second. So let's think about what that is in terms of distance. So if it were going to go a mile, so you see a lightning strike, and let me get it in a color that writes on top of the blue. So if it's 5,280 feet in a mile, times there's 3.281 feet per meter, and if sound is moving at 340 meters per second on a typical day, and that changes with temperature, pressure, humidity, a lot of things make that change from 340 just a little bit. But let's see how long that would take. So 5,280 divided by 3.281 divided by 340, right? It's about 4.7 seconds. Okay, so sound travels about 4.7 seconds. It travels a mile, and I usually do a 5 count. So 1,001, 1,002, 1,003, 1,004, 1,005. You see a lightning strike, you do 1,005, it's a mile away from you. If you see a lightning strike and you go 1,001, before you hear the boom, it's going to shake you because that lightning strike was within a 0.2 of a mile of you. Has anybody had lightning strike very close to them? Okay, what was the sensation? I mean, well, I'm talking a couple hundred yards.
Terrifying.
It's terrifying. You felt a shake. You felt a wave. When I was next to a pole that got struck by lightning, putting out hay on the back of a wagon on a tractor, and all of the hair on my body just stood up everywhere. I mean, it was a crazy sensation. But I didn't hear any gap between seeing the bright flash, and the flash to me wasn't in one place. I had no idea where the lightning bolt hit until we looked up and saw the pole was on fire. To me, the flash was everywhere around me. So, I mean, it was so bright. But there was absolutely no delay in the flash of light and the sound. It just seemed like they happened at the same time. But you can get an idea how far something is in terms of a lightning storm by counting the delay. If it's 15 seconds from the flash, that strike was 3 miles away. Now, light is so much different because where this is traveling at 10 to the 2 meters per second, right? So 3.4 times 10 to the 2, this is 1,000,000 times faster. So light at distances that we think about, again, the light would go around the Earth, go around the circumference of the Earth 2.5 times in 1 second. That's how fast it's moving. And we think that is an absolute constant, that it doesn't change. Okay, so we start looking at waves and start describing how they behave. We look at the height of the wave is one thing. So how tall is that wave? We look at, it's called the amplitude. We look at this in terms of distance from the node to the crest, or node to the trough, so how far it goes up or how far it goes down. Either way, so go back to our, how far is it up here? Or how far is it down here? Those two things, it's a symmetric pattern, so those two things will be the same. And that how high that wave is, or the amplitude, is going to tell us something about the intensity or how bright it is. So the higher the amplitude, the brighter the intensity of the wave of light. Another characteristic that describes electromagnetic radiation is what's called the wavelength. And this is the Greek letter lambda, looks like a little upside down Y. And it tells us the distance that a wave covers in one repetitive cycle. Okay, so if we want to think of it, typically we look at the maximum to the max or the node to the node. So I'll go back to our previous one here. So when we measure something like wavelength, we're looking at how far is it to go from this point to this point. That distance is one wavelength. But if we measured it at the nodes where it crosses the axis, this also would be one wavelength. Now, it crosses going back up, but we've got to get it on the repetitive cycle. So it's going down here, we've got to get it where it's coming back down. So half a wavelength is at 0.2, but it goes up and it comes down. It's a roller coaster. All right, so if we think about The next characteristic that we can look at, so there's our two properties that we just talked about. Our wavelength, describing that, and our amplitude being our height of the two. The third way that we can describe it is the frequency, and it's related to the wavelength. And frequency is given the symbol of the Greek letter nu, so it looks like an italicized V, right? And it's the number of waves that passes through any point in a given period of time. And usually we describe it as the number of cycles per second. So it's the number of waves or cycles that pass in a period of time, which is typically a second. So the units associated with frequency are hertz, and a hertz is simply an inverse second, 1/seconds. So it would be, you count for a period of time and say, okay, in 1 second, how many times does this wave front, how many of these, this being one wave, how many of these come by in 1 second's time? So things like electricity that powers the modern things. Anybody know what's the frequency of electricity that in household United States? 60 hertz. It's a 60 hertz pattern. So it's going up and down 60 times a second. Right, now that's the thing about AC electricity. AC electricity, if you touch it, anybody have ever been shocked when plugging something in? Almost everybody has. With AC electricity, you can let go of it because it's going on and off 60 times a second. So typically, unless it's a very, very strong current, you can let go of something. But when you deal with DC electronics, direct current, that doesn't ever change, it's much more deadly. Okay, because it never goes to the 0 point, you can't ever get away from it. Now, if it's a strong enough electrical current in AC, it's still deadly, and there's no getting around it. But like a lightning strike is a DC charge, much, much higher fatality rate exposed to the amount of energy. So if we look at the total amount of energy that's associated with a light wave, or any form of electromagnetic radiation, it's associated with the amplitude of the wave and the frequency. So the two things are related to one another. The larger the amplitude, the more force it has as it strikes something. The greater the frequency, the more frequent those strikes are going to be. So it's going to hit more and more and more as more times a second as it comes through. Okay, so we have a relationship. Since we know that all waves are traveling at the same speed, the shorter the wave means that the more frequent it's going to pass by a given point. And the relationship is inversely proportional. So frequency is inversely proportional to the wavelength. So frequency is inversely proportional to the wavelength, lambda. And the relationship between the two is c, the speed of light, which is a constant. So what that means is if we know the wavelength, we can calculate the frequency or vice versa. We know what c is. C is known. So regardless of the type of electromagnetic radiation, C is 3 times 10 to the 8 meters per second. But it means if I know one, I can calculate the other. If I know frequency, I can calculate wavelength, or vice versa. If I know wavelength, I can calculate frequency. So the two things are related by the speed of light. So when we look at things that have different colors associated with them, keep in mind that if it's a different wavelength, it's a different frequency. When things have different colors associated with them, the different colors associated with different wavelength. So if I see something that's red, it has a longer wavelength than something that appears that's yellow. So the waves are more compressed now compared to what they are at red. So red is long, yellow it's shorter, and if I go to something that's blue, it's even shorter than that. So with blue, the waves really get short. And if I compare the frequencies would be inversely related. So this one, because there's a lot of waves passing a point, the one on the bottom that has the shortest wavelength, this would be the highest frequency, right? This one would be the lowest frequency because it has the highest wavelength. This one has the shortest wavelength associated with it. Now when we look at the brightness of something, that's related to the amplitude term. So regardless of how big the wave is, these two waves have the same wavelength and the same frequency. They're passing the nodes at the same point, right? But the amplitude, how tall it is now, is what's making the difference of how much force that's coming in here. This one's not very tall. This one's much taller. It's going to represent a brighter beam of light. And so both things play a role, the frequency or the amplitude. Now, color, as we think of color, is associated with visible light. And these are what our eyes let us see uniquely. The photoreceptors in our eyes, they respond to different wavelengths or frequencies, and somehow our brain makes a distinguishing factor between different colors that we see that are the rainbow. And we talked about the colors of the rainbow or a guy's name already. So Roy G. Biv. So Roy G. Biv stands for red, orange, yellow, green, blue, indigo, violet. And those are these colors in order, going from reds at the top to the violets at the bottom. And anytime you see a rainbow in the sky, all the colors are always stacked in that order, every time. Right? So these are going from highest wavelengths in the reds to shortest wavelengths in the blues or in the violets. Now, the thing that we see in terms of colors is that one thing I'll tell you is that the colors that we see are unique. The same way that some of you may like one type of food or flavor or favorite spice, and the person next to you doesn't like it at all. That's because the taste receptors that are in our tongue and are in our mouth respond differently to different chemicals in the food. In the same way, when we see color, we all see color uniquely and differently. The photoreceptors in our eyes respond differently to different colors. Somebody in this room is colorblind. We know 5% of the population on average is colorblind. Most of the people who are colorblind never know it. You've just never been to a situation where you knew there was a different, you see colors different than somebody else. You see a color and some green pops in a painting to you. Somebody else looks at the same painting and the most predominant color they see may be a yellow or a blue. That's the reason art's subjective. Different artists emphasize different colors based on the photoreceptors in their eyes. When you see it, you may not see the same thing that artist does. Right? It differs. It's as different as the flavors in our taste buds. We do a lab, and we may do it this semester, where we go look at light at different colors. And as we look at spectra, we can see how low we can see. And in terms of the wavelengths that we can see, what we think of as the visible region and the Roy G. Biv, some of us can see further in the reds than others, and some of you can see further in the purples than others. I personally can't see anything below 440 nanometers. Some of you can see all the way down to 400. And it's nothing that's due with my old age and becoming blind as I get older. When I was a freshman in college, I still couldn't see it because I did the same thing in college. Some of you can see further up, right? So if you're look at, do all things see the same way? Absolutely not. Some things don't use visible color to see with at all. Some things use infrared. So infrared is the region of electromagnetic radiation right above color. And infrared uses a lower energy. Things like vipers, that category of snakes, they use infrared to see. That's the reason they're night hunters. Okay, so they want to be where the visible light's not so strong. They're finding their prey, whether it's a mouse or whatever it is, based on a heat signature. That's what's associated with infrared. Now, the thing about color, when we look at color, the color of something is due to light being absorbed. Right? If we take white light and we shine white light on something, all the colors are absorbed except for one, the color that bounces back to our eyes. So we're standing here looking at this. This is our eyeballs. And the color that we see that the person, this is a red sweater, is because all the other colors of the spectrum are absorbed and only the red color is reflected back towards the person that sees that. So colors that you see are complementary. We see the colors that not are absorbed by material, but the colors that are reflected off of it. All right, we'll continue talking about light as we go on through the chapter. All right, remember lab tomorrow.